We are going to look at mechanical oscillations, and we know that an oscillation is defined as a to and fro movement, of a particle uh, in a medium or within a medium, or from one point to another within a medium. But also remember to subscribe to Mr. Academia YouTube channel, share our videos, like, and also comment on our videos. So mechanical oscillations are divided into three types. We have what we call the free oscillations, we have what we call the damped oscillations, and then we also have what we call the forced oscillations. So if you look at the free oscillations, the free oscillations are the oscillations in which the amplitude remains constant and the oscillating system does not work against the dispersive forces such as air friction and viscous drag. So meaning that in the free oscillations that we are looking at, so for them, what happens here is that the energy of the system will be constant, and also on top of that, it means that there is no energy that is lost to the surrounding in this type of oscillation. So it also means, or it also implies that when the free oscillation is happening, since energy is not lost, it also means that the amplitude of the system is also constant throughout the oscillation of the system. So the amplitude is constant, or the energy is constant, because the dispersive forces, these are the forces which cause a loss in energy, such as air, friction, and viscous drag. Those forces are not there. That's why the energy and the amplitude remain constant. So if you have to look at the displacement graph for a free oscillation, this is how it is, or that is how it appears. So basically, you can see that the amplitude is the same throughout. The amplitude remains the same throughout the system. Here, amplitude is the same, and the energy is constant throughout the oscillation. So the other type of oscillation is what we call the damped oscillation, and this oscillation energy is lost to the surrounding, and also the amplitude keeps on decreasing until the oscillation dies away, or until it fades. And basically there are dissipative forces which are taking place in this type of oscillation. So the dissipative forces are the forces which cause loss in energy. We have air resistance is one of the forces that can cause a loss of energy in this type of oscillation. So damped oscillations are classified into three. We have what we call the underdamped oscillation. So the underdamped oscillation, it's a type of oscillation whereby for it, for the underdamped oscillation, when the system oscillates, for some time, and then it dies out gradually. Dies out, meaning that oscillation occurs, but with time, the oscillations die out due to the dispersive forces. An example of an oscillation which is under damped oscillation is like when you swing a pendulum bob in air. It oscillates for some time, but after some time, it dies out, meaning that the air resistance causes the oscillation to die out after some time, but oscillations occur. So the graph for an underdamped oscillation is this one here. You can see the oscillation takes place, but the amplitude keeps reducing with time. You can see the amplitude here is different from the amplitude here, meaning that the amplitude keeps reducing with time until finally the oscillation dies out. So examples of such oscillations are swinging a simple pendulum in air, and also oscillations made by a spring which is oscillating in air. We look at another type of a damped oscillation, which is an overdamped oscillation. So an overdamped oscillation, for it, the system does not oscillate at all. Take note of this. The system does not oscillate at all when displaced, but it takes a very long time to return to equilibrium state. The system does not oscillate, but it takes a very long time to return to equilibrium position. So this is an overdamped oscillation. Uh, the graph for an overdamped oscillation is represented as you can see in this graph. So the system does not oscillate, but for it to return to equilibrium position, you can see the time taken is very long. So an example of an overdamped or what we call heavily damped oscillation is a horizontal spring with a mass on a rough surface. So the spring will be pulling the mass, but it will take long to return to equilibrium position, but it will return slowly. Then we have what we call the critically damped oscillation. So for it, the system does not oscillate at all when displaced, but it returns to equilibrium position in a short period of time. There are no oscillations which occur at all, but the system returns to equilibrium position in the shortest possible time. So examples of systems which show this type of graph here for a critically damped oscillation, we have the shock absorbers in cars. We can also have the toilet doors. Some toilet doors are also made in such a way that they don't oscillate at all, but they return to equilibrium position in the shortest possible time. Then lastly, another type of oscillation, this one is separate because we had free damped. Now the third one is what we call the forced oscillations. So these are oscillations which are caused by an external force, meaning that the system has to be subjected to an external force which sets the system into oscillation, and then the system oscillates at, and then when the system oscillates or when the system is set into oscillation at a frequency which is similar to the frequency of the which is similar to the frequency of the system, then we say uh, that the resonance is occurring. That is when the system is set to oscillate at a frequency uh, which is similar to the frequency of the system. That is, if the external force has a frequency similar to the frequency of the system, then that time is when resonance occurs. So basically, a forced oscillation, it's where vibrations caused by an external force and the system oscillates at the same frequency as the vibrating force. An example of a forced oscillation, we have oscillations in a jitter string, we have oscillations of a building that is during an earthquake, then we have oscillations of air column in a music pipe. So these are some of the examples of forced oscillation. So remember to subscribe to our channel. You can also share our lessons, like, and also comment on our lessons. Thank you for watching.